Hi, Moritz. Good to have this chat with you today to talk about Reed-Solomon and random linear network coding, RLNC. You and I, at this point, I think we go way back, but maybe let's introduce ourselves. I'll start. I'm Muriel Médard. I'm co-founder, CEO of Optimum. I hold the NEC chair in software science and engineering in the electrical engineering computer science department at MIT. And that's actually how I met Moritz when he was visiting from Technical University of Munich. And Moritz, if you want to introduce yourself.
Yeah, thank you. First of all, pleasure to have this chat. My name is Moritz Grundei. I have been working on coding for some time now at Technical University of Munich and visiting you at MIT, where we worked on actually error correction coding together. And yeah, today we're going to talk about randomly network coding and Reed-Solomon coding and all of that sort of in the context of blockchain. And I'm looking forward to our chat.
Yeah, me too. Me too. So maybe for our listeners, we can start with what is coding. Some of the people who will be listening to this know full well what it is, might be specialists even. Some of the folks might just be coding curious. And you mentioned that we started working together on error correction, errors, which is data being corrupted, being wrong, and erasures, which is data missing, are unavoidable in the real world. And you need to actually have ways to manage these potentially lethal consequences of having data being wrong or missing. And what does coding do? Coding actually splits the data into pieces. Often in blockchain, we call them shards. And then it adds some redundancy. Effectively, it creates equations. And with these equations, which add extra redundancy, or I prefer calling it repair always rather than redundancy, then we can actually reconstruct the original data. I don't know, what do you prefer, repair or redundancy? How do you like to call it, Moritz?
So yeah, I mean, I guess you were the first person who I heard calling repair. I like that word a lot because it's much more positive, right? It has a positive intention behind it. We want to preserve the information content or in the message, actually. So I guess repair is a much better word.
Yes, yeah, but we will slip back often into calling it redundancy, which is the more common terminology for it. Redundancy somehow sounds a bit superfluous. Repair, as you said, is much more positive. It's like you have to fix it. It's the code is there to fix the real problem. You shouldn't think of it as superfluous. Yeah, absolutely. So, Reed-Solomon, or RS, we hear a lot about it. These codes have been around longer than you and I have been, and even I have been on this earth. They're definitely widely used in storage, in point-to-point communications. I'd love to hear how you describe Reed-Solomon codes.
Yeah, I mean, Reed-Solomon codes, in a sense, they are sort of the prototypical code, like the first code probably you come across when you think about error correction coding or when you learn it in class, for example. So the idea is actually pretty simple, I would think. So given that I have a let's say a polynomial, let's say a function. So the easiest representation probably everyone knows from school is a line. I can describe this line by any 2 points on this line, right? So, but I can also say, okay, I'm gonna not generate 2 points, but maybe 4 or 6 or 8 points. And then when I give these 2, 4, 6 or 8 points to someone else, I can maybe drop maybe 1 point is gonna I'm gonna mess something up and the coordinates are distorted. So I can eventually recreate the original line out of any two correct points in that sense. So I can drop some. This is like the first and probably very simple way of creating redundancy and therefore regenerating or getting the original information back instead of lossy or also lossy environments. So
I like your description, by the way. I think that's much more intuitive. I always use equations because I'm used to thinking in terms of equations, but I like your line much better. It's like if you have a line, all you need is 2 points. If you lose a few, you're okay.
Yeah, definitely.
That's a much nicer way to describe it, much more intuitive. I'm going to borrow that one just so you know. Yeah, and as you said, the core intuition is you're treating the message as a polynomial. I mean, a line is a polynomial. It's just a pretty simple polynomial. It's degree 1. My favorite polynomial for sure. And as we said, you use this in so many different systems, whether it's storage, media. Often this is called forward error correction. And we talked about errors and erasures. There's a little bit of an unfortunate coincidence of the E letter, because sometimes people talk about FEC as forward error correction. Sometimes they call it forward erasure correction. And there's a natural confusion that comes out of the fact that erasure and error both start with an E. It's, there's definitely connections, but they're trying to do different things, right? And if you think of Reed-Solomon codes, of course, they were originally designed for error correction with some properties in mind. Some of them are actually very constraining because they were designed for error correction. And wanted to, hear about your how you view those constraints.
Yeah, sure. I mean, I can share some image here. Give me a second to share my screen. So basically, what we see here, we just talked about redundancy or repair, so to speak. When we think about Reed-Solomon codes, and we see Reed-Solomon codes on the left side, we see that they don't allow you to combine any sort of combination of how much information or how many pieces you want to transmit, either uncoded or encoded, and the rate at which you want to transmit it, like how much redundancy you add to each one of those. So you can see, for example, you have a length n code. So you have, for example, 32 a length n equals 32 code, 32 n equals 32 code, and you have only specific code rates, like redundancy rates, you can add to this code. Like the core underlying reason for this is basically the fact that we have to construct a polynomial in the first place, and we do that over a so-called finite field, which has inherent properties that sort of restrict the length, or like the two properties of the code that define its repair. And we see, on the other hand, that when we think about like purely random ways of constructing codes which are not defined by polynomials, we don't have these constraints, right? So we see here that sort of any combination of code length n and pair are possible, which is just a very, very illustrative thing that
Yeah. It on the left-hand side, and just to remind our listeners, the rate here indicates what percentage of the transmitted data is actually payload. So 1 means that the rate is including absolutely no repair/redundancy. All of the data is payload. And so as you have a lower rate, you have more redundancy. So you have more ability to fix, as we've talked about. But on the other hand, it comes at a cost of transmitting data, which is not information bearing. And as you show, by the way, I want to thank our colleague, collaborator, Moritz, and my collaborator, Ken Duffy, who's the chair of the math department at Northeastern University here in Boston, who first came up with this very nice way to visualize what coding is doing. But yeah, what you see on the left-hand side is it's almost all white space. It's basically space that is not available to you for design, right? So it's a really, really constraining thing to be working with codes where you're artificially restricting yourself to basically giving up on most of the design space.
Yes, totally.
Yeah. So no, thank you for walking us through that picture. Now we've been talking right now about Reed-Solomon, which, as we mentioned, was really designed originally for a point-to-point system, meaning there's a single entity node, user who does the coding, and it sends it to one node that does the decoding, that reconstruction, fixing that we've talked about. But of course, in a network, you don't just have one sender, one receiver. Well, you could. That's the world's simplest network formed by a single link. Not very exciting, not exactly blockchain ready. And to be able to think about a network at large, then you really need to figure out how the information is being managed within the node. Now, you could just, put blinders on and pretend that the entire network is a single link, but you'd be losing so much because effectively you're pretending that the network is not there, and you're not taking advantage of the potentially really rich topology and capabilities that the network is giving, right? It's like you have this square peg, which is the Reed-Solomon code. You have this round hole, and you're just going to take a hammer and pretend it goes in, right? And we know that that's not the best thing. And so, again, going back to restrictions, is not just restrictions in terms of that design space that we just saw, that's, vast white space of, unused design area. But it's also unused space inside the network because the intermediate nodes are not contributing to the overall repair, maintenance, effectively robustness and efficiency of the data. And I wanted to hear how you describe how RLNC, which we mentioned at the beginning, is randomly network coding. And of course, you just showed in that figure some random coding. It was not network coding. It was at a single node. But how RLNC changes this, how you explain it again to your colleagues.
Yeah. I think the point to start here, if we started RS, is that we really talk about a different problem definition at this point, right? You mentioned it. We were talking also in the example that I gave about, I'm going to give you data, I might drop some of it might get corrupted. That's the typical point-to-point link, right? DVDs or similar point-to-point channels we've seen in communication systems. Now, when we talk about networks, things are different, right? Because the coding operation, we can in theory still use something like Reed-Solomon code, and we would only use coding at the edges, but we don't use all of the intermediate nodes, which might also participate in the coding operation, and therefore might also help in sort of recovering erasures. On network level, we mostly talk about erasures. packets being dropped, packets getting lost. And random linear network coding is a very unique kind of network code in that it just says the way we do coding at intermediate nodes, also at edge nodes, is basically random. Like, we don't really give the nodes any instructions on what they do. They just form random equations, recombine them, and then send them along. Because you might think about, yeah, well, now if the whole network does coding, how does everyone even know what they have to do, right? But random linear network coding says just combine packets randomly, and you're going to be fine in the end. And this is a huge saving in complexity, and makes the whole system so simple. But I guess you are the best person to talk about it in a sense, because it's been one of your let's say longest standing works, random linear network coding, going
That's
back
right. Yeah.
to the early 2000s.
Yeah, yeah, absolutely. And actually, I remember when we were working on this, along with wonderful collaborators, including one from TU Munich. Well, at the time it was the University of Illinois, Ralph Koetter, and my student Tracy Ho, and many other wonderful colleagues. I remember that we got so much pushback because people really thought that you had to be able to do better by being very, very clever. And, that somehow if I had more information, if I had state information about what node was doing what shard was at which node, surely you can do better than just choosing coefficients randomly. And, by randomly, we don't mean with some sort of perfect pseudo noise sequence at all. Randomly really means just, not in weird constrained ways that might work wrong, basically.
Yes.
And that there was a lot of pushback because it seems counterintuitive. But as you say, it's very simple. It's kind of funny. It's very simple from a implementation perspective. It's definitely extremely suitable for something like blockchain, which is decentralized. But conceptually, it really requires a leap of faith. And, people tried so much to do things instead. Well, could you take a Reed-Solomon and change it? Could you take other kinds of codes? I mean, we've talked about Reed-Solomon, but of course, many other, let's say, traditional codes like fountain codes would be transform codes, Raptor codes, and so on, which are a little different in that they adapt on the fly how much redundancy or repair they put in. But all of those codes are still end-to-end, as you say, at the edges of the network. And I think, to me, what's most surprising is that RLNC is not just Optimum, but that the difference between the Optimum and the sub-optimum, like a Reed-Solomon, like a Raptor, is not 5%, 10%. I mean, sometimes you're like, okay, it's not Optimum, but who cares, right? I'm close enough. It's exponentially growing as your network gets larger. I'd love to hear how you describe the intuition for why that is. Because I think you always have such good ways of describing that.
Sure. I can share like another short image of that. So we've been talking about the difference of encoding end-to-end versus using or leveraging the entire network to do coding, and that is really where the core difference especially in throughput is taking place. So we can look at like a very simple example, right? So we have two nodes which want to communicate a message, and the message has to traverse through, let's say, two other nodes, right? So we have these two purple nodes. And in the one example, we use a typical end-to-end encoding. And in the other example, we use a network code, or like a random linear network coding, which actually uses these intermediate nodes to do, let's say, additional coding, or to do coding themselves. So what we see in the first instantiation, when we have end-to-end coding, is that losses compound, right? We talked about coding being this idea of adding, how do you say it? Adding repair, adding redundancy. And this redundancy, if we think about erasures, is getting lost along the way. So that if I wanted to securely transmit a message from A to B in an end-to-end coded setting, I would have to account for the entirety of the losses that happen along the way to make sure that the message is arriving at the end. Now, what happens in random linear network coding, or when we use coding at intermediate nodes, call it recoding, is that every one of those nodes kind of does its own coding operation, in a sense. So the quality, or the losses, don't compound over the entirety of the path from source to sink, but so the overall quality is kind of the quality of the weakest of those links. So in that sense, we have, in the first example, we have 37% of losses. And in the second example, we only have 10% of losses. And this is really the, if you think about it, if I make the chain even longer, then in one example, with each and every hop, I have to add more and more redundancy in the first place. While in a second example, it doesn't matter, right? So the chain can stay, can get as long as it wants. I still only have to add the same amount of redundancy up front if I really want to make a safe transmission here. And this is sort of where one of the core advantages of random linear network coding lies. But please.
Yeah, absolutely. No, I think you explained it beautifully, and I think you mentioned compound. It's really the difference between simple interest and compound interest.
Yes.
And they grow exponentially apart. That's the whole power of it. And so with random linear network coding, you can do what you mentioned, that recoding, because you can basically create codes on the fly from whatever coded pieces, whatever equations you have. You can make equations out of old equations without having to recover the original data. Whereas in traditional systems, traditionally coded systems like Reed-Solomon, you actually have to get back to the original data. So you can either just forward along, or you have to decode, recover the original data, and start over again. And that separation, which looks almost like a subtlety, just a technical subtlety, is actually massively powerful. And so it's not like, oh, it's all close to as good. No, it's exponentially worse to do a Reed-Solomon code. And again, this was something which early on I think a lot of people had trouble getting their heads around, because it seems so counterintuitive. But you can try it out and see right away the difference. It's it kicks in very, very quickly. So thank you for stepping us to this. So okay, so we've talked about RLNC encoding, Reed-Solomon coding. I should mention that the recovery is what we usually call decoding. We talked about that repair. That actually is very simple for erasure codes. And you can decode a Reed-Solomon or RLNC or anything else always in the same way. You basically just have this reconstruction from a bunch of equations, and it's very fast, it's very simple. And so the decoding itself for these erasures is actually quite universal, right? It's the same decoder. that you can use for all of those. So you can mix and match and still keep the same decoder. So we have just a few minutes left. I want us to jump to the blockchain applications, right? So we've talked about the fact that RLNC is decentralized. A priori, decentralization goes really well hand in hand with blockchain. But let's talk a little bit about where coding shows up right now. Of course, we're both at Optimum, and we are using MonP2P, which is RLNC-based gossip, where I've been working with Ethereum validators. We're going soon on to just a few weeks. We're going to mainnet, which is extremely exciting. Traditional, as we mentioned, some optimal codes are used, for instance, in Solana with Turbine, Rotor, which is the next version that's coming up in Solana with Alpenglow is also going to be using Reed-Solomon. We mentioned Raptor codes, Monad uses those. Wanted to hear a little bit your view of why this matters in blockchain.
Yeah, I mean, I think there's actually two interesting kind of sort of applications of coding in blockchain that we've known so far. So one is like really the obvious one, right, that we've just talked about, which is propagation of payloads. If we talk about Ethereum, we think about either blocks or also blobs. Nowadays, blob columns. And if we the other kind of application is really what we call data availability sampling. Now, sticking with block propagation so far, I would think there is two kind of different systems. There's one sort of the permissionless meshes, which is or network meshes, which is Ethereum would be an example for that, and the other one would be more of a structured broadcast architecture where you have a permission set of nodes. Ethereum, Solana, or Monad would be part of that, and a more, let's say, structured tree along which the messages are propagated. Now, coding is useful in both of those cases, and we have built with MonP2P the first gossip protocol that uses RLNC, first for Ethereum, and we have seen amazing gains in that sense. So talked about with Sajida last time about the latency improvements that we've seen on Hoodie. And the reason why this is important is several-fold. I mean, I guess you can talk about it from a commercial perspective much more than I can, but we've seen, especially in these last couple of months, that the Ethereum network has, for example, been put under strain by a lot of new messages being produced, especially in the context of Fusaka, with blob columns being propagated. So it needs faster data propagation, and coding is the number one tool to do that, and RLNC the optimal one. But yeah, that's about the.
Yeah, no, that's great. That's a great description, and also, as you said, sort of it's inherent to the need for scaling, right? As we said, one is scaling, in a way which is getting exponentially worse, and ours is scale free, right? And you can't beat that. You can't beat scaling. You can try. You also mentioned DAS. I wanted to just spend a couple of minutes talking about the data availability.
Yes, this is like the second kind of application of, which is also like an interesting one, quite counterintuitive. So the idea is that I want to have a way to check if some data is available without actually downloading it, which sounds kind of counterintuitive, because the easiest approach would be, let's say you have some data and I just ask you if you have it, and if you do, then I just then then I just believe you. But we, in a trustless environment, I need to get some confirmation, right? Some sort of proof for that. And the idea is that usually in the beginning, people used Erasure codes, like also Reed-Solomon codes, to say, okay, if I get just a bunch of just some coded pieces, then I can be probabilistically sure that I could, if I wanted to, download the entire thing. And the basic premise behind this is that if enough people were to sample coded pieces, then you would have to withhold at least a certain percentage of pieces for me to be for us to be unable to decode, and therefore I would detect that. So it's like I'm asking you for some information, and I'm not asking you directly for it, but for some encoded version of it. And in order for you to not give it to me, it's very unlikely that I'm not going to catch you. So
just to interrupt, the way I like to describe it, I don't know how, it's like, so my mother was a history professor, and suppose you had to do a history exam, and rather than ask somebody what was the date of this battle and the date of this and the date of that, you go, just give me the sum of the dates. What is the likelihood, unless they know each and every date, that they're going to get the sum correct?
Yeah, that's a pretty good description. I mean,
it's like the one question exam.
Yeah, exactly. So
no partial credit.
Yeah, and I think it's actually a pretty good analogy. So if we think about, and now we come back to Reed-Solomon fixed rate coding again, these kind of codes, they give you sort of a fixed set of questions you can ask.
That's right. You can only ask the sum of the dates, and that's it. And yes. Of course, pretty soon the students will learn that you do that and learn that one thing.
Yeah, definitely. And also here, like one thing that we've also been looking into is, what if you actually make that question space, if you want to stick with that metaphor, what if you make that flexible?
Right.
So now what happens if I actually tell you which dates of the battles you have to sum up, and you have to answer me? And this is essentially what random linear network coding does. And I also have an illustration for that. So
yeah, absolutely. Yeah, it's like, give me 5 times the year of the Treaty of X with 2 times the Battle of Y, and
Exactly. So the idea here is, now we have usually systems in use today use fixed rate codes. We've seen systems with LDPC codes and also 2D Reed-Solomon codes.
By the way, we haven't talked about LDPCs, but they're yet another of these classical codes
exactly.
out there. Yeah, they were actually invented by my doctoral advisor, Bob Gallagher. It was in the 60s. It was his doctoral thesis. Yeah.
So yeah, you can go like, this is 1960 exactly, Reed-Solomon code, and this is 1967 or something.
62.
62. Okay, yeah, that's interesting.
Yeah. And actually, the kinds of codes that are used in which are product/tensor codes that are used, for instance, in Celestia and these systems, are actually invented. Even though the Reed-Solomon was invented later, the general format of the code was invented by Bob Gallagher's advisor, also at MIT, who was Peter Elias. So there's a line there.
Yeah, it's all intertwined. RLNC to the
yeah, it's all in the academic family. Yeah.
Yes, definitely. So what we basically see here is that, staying in our metaphor, these are like the number of questions that I have to ask if I want to check data availability, and this is the probability that I'm going to get they don't get fooled, right? That I'm gonna.
Yeah, the student didn't actually know, but gets lucky.
Exactly, just gets lucky that I answered a question correctly.
And by the way, this is a logarithmic scale, right? So you're multiplying by 10 every time. So a change here, it actually shows a huge gap.
Yes, so this would be 10% probability. This would be 0.001% probability.
Yeah.
And what we see here is basically I can get to the same kind of certainty about data being available by just asking 2 questions, as if I were to ask 70 questions from the predefined set or 150 from the other predefined set. It's like I can either ask real novel questions, and the student has to actually learn and understand the material, or I ask like a huge amount of previously, let's say, preparable questions. And sort of my confidence in the student actually knowing what's going on is going to be the same. So
Yeah.
I might be better off just asking two really
two smart questions rather than a whole lot of not so well designed questions. Absolutely. We should probably wrap up. We've gone way over because we've been having fun. I don't know if you had any parting thoughts. I mean, my view is, Reed-Solomon codes are excellent for the job they were designed to do a long time ago. They were never meant to be used in networks. They were never meant to be used in blockchain, and never meant to be used in a decentralized way. There really is a good reason for using the best tech. Not just because it's cool and you want to have the nice and shiny thing, but it's a big difference between approximating 1960s technology and doing the latest and greatest. But I'm biased. I guess you're biased too, but I'll let you talk to.
Yeah,
I'll let you share your bias. I've shared my bias.
Yeah, it's actually interesting to see again the kind of line that goes through RS, or like product code, embedded RS, LDPC, and then RLNC all developed kind of at the same chair, if I remember.
Yeah.
And I think the thing that we really need to that I would want to stress here is the thing about problem statements, right? I mean, we're really talking about different kind of problems that each one of those codes solves in the end. And RLNC is mathematically optimal for the problem of recovering erasures in networks. And that's why we build MUM P2P. And that's why we can also, why we expect, why the performance of RLNC scales so well in the networks that we encounter in blockchain systems.
Yes, so when we say we're Optimum, it's actually provable.
Yes.
How often can you say that? No, I really am Optimum.
Yeah.
Moritz, that was so much fun. Thank you so much. And I hope our listeners enjoyed this conversation as much as we enjoyed having it. And we'll generate conversations locally. And as always, please follow us on X. Go to our website to see some of the latest and greatest, and stay tuned for Mainnet.
Thanks. Bye-bye.
Thank you.